Okay, Calc 2 students, I'm going to re-record this. When I posted 10.6, it looks like the audio was not working, so I'll just give it another try. All right, so let's look at absolute and conditional convergence is the last series test that I want to look at. So reading the definition, it goes like this. If the series of absolute values converges, then we would say the series itself converges absolutely. So when you do this test, you're going to take the absolute value of the original series and see if it converges. If it does, there's your conclusion. Okay, the other possibility is you might do the series of absolute values and it diverges, but the original series might converge. Then we're going to conclude that it converges conditionally. So there's a couple of examples that are pretty simple just to show and are easy enough to do in your head to illustrate this. So if you look at this particular series right here, this is an alternating series, and this is an example of one that's absolutely convergent. And the reason is because if you did the absolute value of this expression, well, what would happen is this term right here would become positive. So instead of alternating from -1 to 1 and so forth, it would just become 1. And you might recognize that this is a p-series. And remember, a p-series, you have 1 over k to the p, and it converges when, that's something you want to know, when p is greater than 1. So that 2 is greater than 1, therefore that converges. So we would conclude that this converges absolutely. So if you think about this, in this case, removing the alternating signs by doing the absolute value does not affect the convergence of the series, so we consider that to be converging absolutely. Okay, the other possibility would be this one, and you may recall a couple of things. We learned a couple of things. 1 over k is a harmonic series, and this harmonic series is known to diverge. However, if you do the alternating harmonic series, okay, it converges. Okay, so what we're going to do is going to take a look at this then. So if we did the absolute value of this series, well, that again would take away the alternating signs, leaving you a harmonic series. Therefore, we know that would diverge. Okay, however, the original series, if we just did the series -1 k plus 1 over k, which is a convergent alternating series, or convergent harmonic series, that would converge. Therefore, we would conclude that this one converges conditionally. So what happens is we know that diverges, but we know the original series converges, so we're going to conclude that that converges conditionally. And one way to look at that is the alternating signs. If you remove the alternating signs, it does affect the convergence. So that series is considered to be converging conditionally. Okay, so we'll go ahead and we'll start kind of analyzing some of these things down at the bottom. So what we're going to do on these problems is just see if they converge absolutely or conditionally, or perhaps they diverge. Okay, so the first thing you want to do on this is we want to go ahead and take a look at the absolute value on here. So I'm going to go ahead and start this like this. So we have the series k equals 1 to infinity. And we're going to go ahead and just take the absolute value of this and see what happens. Okay, well, what's going to happen on this, if you wrote out the terms, you don't necessarily have to do this, but you would have -1 to the first plus -1/3 to the second. What's happening? -1/3 to the second, -1/3 to the third, and so forth like that. You're going to see that what happens, you're going to end up with a negative term, a positive term, and a negative term, and so forth. So it's going to alternate on that. So if we do the absolute value of this entire thing, then we're just going to get all positive terms. So if you go through and work this out, then you can rewrite this as just 1/3 to the k. And we need to see if that converges or not. Okay, well, what kind of series is this? This is a geometric series. It's got the structure AR to the k, where R is the ratio, the common ratio. And we know that the condition for convergence is it converges if this ratio is between -1 and 1. So we would say since we have a geometric series and -1 is less than 1/3 is less than 1, we would say therefore the series converges. Okay, and that's how you would state that. I mean, there really isn't anything to show on your paper, but you do need to state that it's a geometric series and the common ratio is between -1 and 1, therefore it converges. So then basically what we would do is we would go ahead and just say therefore the series, and let's write it like this. We're going to say therefore since the series of the absolute value, since that converges, then therefore we can conclude that the series a sub k will converge absolutely. Okay, so that's how you want to write that then. All right. So let's just write this kind of like this. I'll just state that the series that we're analyzing, -1/3 to the k equals 1 to infinity, we'll say that that converges absolutely. Okay, so that's a pretty simple, straightforward example. All right, and what you want to do generally on these problems, you can start off by just taking the absolute value and see if that converges. If it converges, you're done, and then we can draw our conclusion that it converges absolutely. Okay, and then if it diverges, then we'd have to go on and see if it possibly converges conditionally. Okay. So let's go ahead and take a look at next page. And let's see what we're getting ourselves into on this one. Okay, so what I'm going to go ahead and do on this one then is I'm going to go ahead and let's just test for the absolute value first of all. So let's go ahead and start by just doing the series k equals 2 to infinity. And let's do the absolute value of -1 to the k over ln of k. All right, so we're going to look at that. Now remember, what we're doing on this now is we're testing for absolute and conditional convergence. So we're just going to follow what this tells us to do. So this thing is either going to converge or diverge. We're going to try to show which it is. Okay, so again, what would happen on this is it would just remove the alternating signs. So what you would end up analyzing here is you would end up looking at the series k, it goes from 2 to infinity of 1 over ln k. Now we got to think about all the series tests that we've learned and see if we can figure out something on this. This was actually a pretty good example of a comparison test. So I'm going to pull up the comparison test and let's refer to that and remind ourselves of what that is. If you're doing a comparison test, you're choosing a series that you know something about. You know, you either know that that series you're comparing to it converges or diverges. Okay, so what we're going to do on this one, I'm going to kind of look at this way. So first of all, a sub k, we're just going to say that's the expression 1 over ln of k. And then b sub k, let's try something like 1 over k. Okay, and what we know on this, we know this is a harmonic series. And we know that a harmonic series diverges. So I'm choosing that so I can compare it to that. Now, what we're going to do is we're going to compare it to a divergent series. So what we have to do is we have to really show that this inequality is true. All right, so if we can show that a sub k, all the terms in a sub k are larger than all the terms in b sub k, then since b sub k diverges, then we can conclude by the comparison test that a sub k also diverges. Okay, so what we need to do is we need to show this then. Okay, so we're going to show that really the b sub k term is all positive terms, but at the same time, that's going to be less than or equal to all the terms in a sub k. So we need to show that mathematically if we can. All right. So there's a couple of ways to do this and look at this. One thing is, let's just go ahead and look at b sub k. All right, so first of all, if you write out the terms in a harmonic series, and we're just going to go from k equals 2 to infinity, we would have 1/2 plus 1/3 plus a fourth, and so forth like that. Okay, so that's always positive terms. So we would know that all the terms are greater than 0. Okay, let's look at a sub k. So a sub k, and again, we're going from 2 to infinity. So if we look at, again, we're doing the absolute value, so we're looking at this term right here. So if a sub k, if we were to do just write out the terms on this, okay, the terms on a sub k, k equals 2 to infinity of 1 over ln k, well, we would have 1 over ln 2 plus 1 over ln 3, and so forth. Okay, now what happens on a logarithm is this. This is sort of a review over on the side here. If I was to go through and just graph the natural logarithm function on this, sometimes a logarithm's negative, sometimes it's positive. So if I just do a standard window on this, notice that we're starting with k equals 2, and we got positive terms. So what's going to happen is, remember that the ln of 1, if you were doing that, would be equal to 0. But once you get past the ln of 1, then you're going to have positive terms. So this is all the terms in that are going to be greater than 0. So we know that. So really what we need to do is just kind of think about this. Let's just write down what this is. B sub k is 1 over k. And we want to see if we can show that all the terms are less than all the terms in B sub k, or in A sub k. So A sub k is 1 over ln of k, like that. Okay? So we want to take a look at that and see if we can prove that. Okay, so what I'm going to do is I'm going to show you a couple things graphically, just to kind of get a sense of what's going on. Okay, so what I'm going to do is I'm going to graph 1 over x and 1 over ln of x. Now if you look at this doesn't prove anything, but you can see that 1 over x, all the terms in there appear to be lower than all the terms on 1 over ln of k. What I'm going to do on this is I'm just going to cross multiply this. So I'm going to get 1 times ln k, I get ln k. Hold on, I don't really need to do that. Actually, if you look at this, what happens, and we've talked about this a lot in comparison test, that k is always a larger number than ln of k. If you take the ln of k, you get a smaller value on that. So that is always going to be true. Okay, and that just means you have a larger denominator. So since that's true, then that would show that this inequality is always true. All right, so we conclude that's true on that then. Okay, so what that means then is, since we just showed that 0 is less than b sub k, is less than or equal to a sub k, and remember, we're only worried about k being greater than or equal to 2. Okay, that might not be always true if for k is less than 2. All right, so we got that. So we would say, therefore, we would say a sub k, that series is going to diverge by the comparison test. Okay, so that takes care of step 1. So what we need to do now is, if you look at this, we need to go on and analyze the series a sub k and see what happens on that then. So we go to step 2. Now we're going to just analyze the series k equals 2 to infinity, negative 1 to the k, all over ln k, not doing the absolute value. So we're going to take a look at that then. Okay? Well, this is an alternating series. Okay, so we need to kind of refer to the alternating series test. So let me bring down this. When I'm going over this, I always like to just show you that you always refer to whatever that test tells you to do. So if we're going to show the convergence on an alternating series, you got to show the terms are non-increasing, and you got to show the limits equal to 0. Okay, so I'm going to kind of branch off and do these two things then. So first thing is, we're going to see if the terms are non-increasing. Okay, so we got to look at this particular inequality here. Okay, now remember what we're doing here is we're disregarding the signs. So we're just kind of taking that off, and we're only looking at this piece here. So that means what we need to do is we need to show 0 is less than 1 over ln of k plus 1. And then that is less than or equal to 1 over ln of k. If we can show that, then we know that that's going to be we're going to have non-increasing terms. Okay, so we're going to go ahead and work with that a little bit. Okay, well, you know the terms are greater than 0. If you're doing, since k is bigger than 2, if you do a ln of any number bigger than 1, you get positive numbers. So we know that that part right there is true. Okay, so really all we got to do on this is this, and you see this a lot. This particular number is always bigger than that number. So we could say, since ln of k plus 1 is larger than ln of k, for k greater than or equal to 2, then this would be bigger. The idea is when you have a bigger denominator, your numerators are both 1, then this is true. So then we would say 1 over ln of k plus 1 is always less than 1 over ln of k for k greater than or equal to 2. Okay, so we know that. All right, so now we move on to the second thing. And the second thing is we need to do this limit. So let's go ahead and do the limit. As k goes to infinity, again, we're disregarding the alternating signs. We're just looking at 1 over ln of k. All right? And this is one of these things that's pretty obvious. I mean, this is going to get bigger and bigger without bound. So this is really 1 over infinity. So therefore, that's going to 0. Okay, so then what we would conclude then is we'd say, therefore, the series, negative 1k over ln k, from k equals 2 to infinity, converges by the alternating series test. Okay, so we have that. Okay, so now we're ready to draw the conclusion. So the final conclusion goes like this. Okay, so I'm going to state this kind of like this. Okay, so basically, I'm just going to write the absolute value, negative 1 to k, over ln k. We're going to say since this diverges, and the other series, without the absolute value, converges, then we'll say, therefore, the series converges conditionally. Okay, so that's how that goes, all right? Now, it's just a little bit when you're doing this, the kind of the key things is you need to be able to explain certain things in here as you're doing this, that you're proving this then. So to go over that again, really what we were doing is when we did the absolute value of this, I think we ended up doing a comparison test. So on the comparison test, what we really had to do is compare it with a series we know something about. In this case, I chose a divergent harmonic series. So it really was enough to show this inequality. And really showing this inequality is just, okay, this is a bigger denominator. Okay, and since that's a bigger denominator than that is, then it's true. Okay, so that is enough to explain that this series of the absolute values would diverge. Then we went on and looked at the series without absolute value. This was an alternating series test, since it's an alternating series, so we have to do two things. Show that the terms are non-increasing, which we did, and then show the limit. Okay, so that will take care of that. Now I think we're going to look at one extra illustration on the next page then. Okay, so I'm going to do one more example, and let's take a look at what's going on this series then. So we have another alternating series, and we're going to start this off pretty much the same way. Let's start off by going ahead and do the absolute value. So we're going k equals 1 to infinity, absolute value negative 1 to the k over k squared. k to the 6 plus 1. Okay, so we're going to analyze that and kind of see what we got going on here. Okay, so let's see. Of course, all this is going to do is that's going to remove that part. So what we're really going to be looking at is the series k equals 1 to infinity. And after we take the absolute value of this, we're going to end up having this. Now see, think about this a little bit. This term right here is always going to be positive because you're squaring something. Now you don't have to explain this. This is something I think is pretty obvious. Same thing in the bottom. If you take something to the 6th power, if you take a positive number from 1 to infinity, that's going to be positive. So you don't really need the absolute value symbols after you take that off. So that's really the series that we're going to go ahead and look at then. So what we're going to do is this one, to me, anytime you have a like a rational function and then you got powers of k, the limit comparison test is probably the right choice on this. Okay, this is just kind of set up for a limit comparison test. So let me pull this up and let's kind of remind ourselves what we do. So what you want to do is you want to find a series that you know something about, you know whether it converges or diverges, and then you want to formulate a ratio and then do that limit. Okay, and then you want to see what happens on that. So there's 3 things that can happen. If you formulate this ratio and you get a limit as k goes to infinity and you get a finite number, then a sub k will do exactly what b sub k does. So they either both converge or both diverge. If you found that the limit was 0 and b sub k converges, then you could conclude that a sub k converges also. And if L went to infinity and b sub k diverges, then a sub k diverges. So you just follow exactly what that says to do then. Okay? So my thought process on this goes a lot like this. Okay, if you're going to infinity, this 1 doesn't have a very big barrier on what's going on. So you can just kind of disregard that 1 and think about what's happening if you had this. Okay, well that would be k to the 2nd over k to the 3rd. So that's 1 over k. Okay, now that right there is a harmonic series. So let's use that as our b sub k. And let's just see kind of where this leads us then. Okay, so here's what we're going to do. When we formulate this, let's go like this. Okay, so a sub k is just going to be the expression k squared over square root k to the 6 plus 1. And then b sub k, let's do 1 over k, which again is a harmonic series that diverges. Okay, so we got that. All right, so let's do exactly what this tells us to do then. Let's formulate this ratio. So let's go ahead and do the limit of a sub k over b sub k. And we're going to take that limit as k goes to infinity. Okay, so let's formulate that ratio. So we're going to have the limit k goes to infinity of a sub k, which is this. And then we're going to divide by 1 over k. Well, if you divide by 1 over k, that's the same as multiplying by k. So you don't have to show that step or anything. You can just formulate the ratio like that. Okay? And then let's see kind of what's going on this problem then. So it looks like what would happen is you would have the limit as k goes to infinity of k to the 3rd over k to the 6 plus 1. Okay? Now this right here, again, it's okay if you do this, because this is pretty obvious. If, basically what would happen is this is approximately the same thing as the limit as k goes to infinity of k to the 3rd over k to the 3rd. Again, if you disregard that 1, because you're going to infinity anyway, then this thing is going to clearly go to 1. And that's good enough to state that, because you don't really have to show that with L'Hopital's rule. This is a infinity over infinity limit. You could do L'Hopital's rule, but it's not necessary. It's good enough to do this. Okay, I'm okay with you doing that. So that goes to 1. So what that would mean then is that would be condition 1. So that means since b sub k diverges, so does this. So therefore what we would say is since b sub k diverges, then we could say therefore a sub k also diverges, and then state the test. And we'll just say by the limit comparison test. So we've done half of what we need to do here. Okay, so again, what we just did was we showed that the absolute value of this series diverged. So now what we move on is we're going to analyze the series without the absolute value and see if it converges, and if it does, then we have a conditional convergence. So we go on to step 2. Okay. All right, let me show you kind of what you can get into on these two. So what we're going to do now is we're going to work with the original series without the absolute value. Okay, now what kind of series is this that we're getting ready to analyze? Yes, that's an alternating series. So that means we need to work with the alternating series test. All right, so I mean, that's why. That's the why on that. Okay, so we need to work with this. There's two things we got to do. Show the terms are non-increasing, and then show the limit 0. So we got to do those two things. So let's go ahead and let's start, and let's see if we can show that the terms are non-increasing. Okay, now what I'm going to do in this case now is we're going to go ahead and look at, remember when we do the alternating series test, we disregard the signs, and we just look at this piece right here. So we need to show this basically. We need to show that 0 is less than k squared over k to the 6 plus 1. And then, whoops, I've got to add 1 to that. So I'm sorry, I'm not paying attention here. So we're kind of looking at the next term in the series. So that would be k plus 1 to the second. And then all over the square root of k plus 6. Or no, k plus 1 to the 6th plus 1, and then that's less than or equal to the original. Okay, so we're going to need to verify that that's true. Okay, well, one way you can do this is just with some basic calculus stuff here. So what I'm going to do on this is it's not real obvious that this is true. Okay, I mean, the denominator is bigger, but so is the numerator. So to me, it's not real obvious. Okay, so what I'm going to do is I'm going to model this with a function. So we're going to say, let's let f of x be equal to the function x squared over the square root of x to the 6th plus 1. Let's do the first derivative test and see where it takes us. So we're going to do a first derivative on this. Okay, so let's go ahead and let's get this put together. So we're going to have f prime of x. We're going to use a quotient rule. So we do the bottom, x to the 6 plus 1, times derivative of top, which is 2x, minus the top. Derivative of bottom is a chain rule, so we'll do 1/2 x to the 6 plus 1 to the negative 1/2 times the derivative of the inside part is 6x to the 5th. And then all over the bottom squared. So we do x to the 6 plus 1 squared like that. Let's clean it up and let's see where this leads us then. And sometimes you got to do this. Okay, it's not real obvious that this inequality is true. So let's go ahead and see what we get here then. So I'll just write this as 2x square root of x to the 6 plus 1. Over here it looks like there's a couple of things we can simplify. There's 6 over 2 is 3. X to the 5th times x squared is x to the 7th. So it looks like we're going to get minus 3x to the 7th times the square, whoops, hold on, that's a positive exponent or a negative exponent. So let's just write this like this. You can do this in your head. You can move that down to the bottom and turn that back into a radical. And then the bottom squared, you're squaring the radical, so you would end up getting x to the 6 plus 1 like that. Okay, so let's continue to simplify this. So the next suggestion I would have is let's get rid of this fraction. So let's multiply the top and bottom by square root of x to the 6 plus 1. Okay, like that. All right, now I'm going to move this up here and then kind of finish this up here. So let's move this up here. And what we're going to have now is we're going to have f prime of x is equal to, I'm going to do a distributive property. You can do all this in your head. If I square those two radicals, you're going to end up with 2x times x to the 6 plus 1. Radical's going to go away. And here it's going to cancel, so you'll have minus 3x to the 7th. And then the bottom, let's just leave that alone. Okay, clean it up a little bit and see what happens. So it looks like we're going to have 2x to the 7th plus 2x minus 3x to the 7th over this. And we got some like terms we can put together, so now we're ready to kind of see where we're at here. So it looks like we get the first derivative, f prime of x, is equal to 2x minus x to the 7th over x to the 6 plus 1 times the square root of x to the 6 plus 1, like that. Okay, so we got to show that this is decreasing, so we have to show that this derivative is negative for k greater than or equal to 1. Okay, because our series starts at k greater than or equal to 1. Well, there's several ways to show this. Okay, one thing that'll happen on this, if you did like you could do a critical point if you wanted to, or you can just kind of see this. This actually is not too hard to see in your head, so I'm okay if you did something like this. Well, if x is greater than 1, greater than or equal to 1, then you would end up having a negative numerator. Okay, now what will happen on this, it wouldn't happen at 1. So what would happen on this is if x is equal to 1, you would have 2 times 1 minus 1 to the 7th, so that would be a positive. If x was equal to 2, you would have 2 times 2 minus 2 to the 7th. Well, that's clearly negative, and it'll be negative from then on. So what we could state then is we could say k greater than or equal to 2, then what we would have is a negative, and you can tell the denominator is positive. I mean, you don't even have to explain that. You've got even exponents, so it'd be negative over positive, it'd be negative. So if k is greater than or equal to 2, then the first derivative would be negative. Therefore, we would have decreasing terms. And that's okay if you can show it doesn't have to be increasing for every single term. Once you get to k equals 2 and beyond, then it's decreasing from then on out. So that's okay. And then the second thing we're going to do is we're going to do, by the alternating series test, we're going to go ahead and do the limit as k goes to infinity. Again, just don't look at the alternating sign part, just look at this. And this one's going to be pretty obvious. Okay, so we have this. Again, what you can do on this is you can just say, for all practical purposes, this is the same as k to the second over square root of k to the third as k goes to infinity. So that's going to be about the same as the limit of k to the second over that was a k to the sixth, wasn't it? I think I'm thinking ahead here a little bit. Okay, so I got this, so that would be about the same as this. Okay, that would reduce down to the limit 1 over k. K goes to infinity, so that would be like 1 over infinity. That's 0. Okay, so we've done both of those two things right there, so now we can just state our conclusion. Okay, so we got that then. All right, so what we would say then is, therefore, by the alternating series test, we just showed that this series, this alternating series that we're asked to analyze, we can say that this converges. Okay, and when we put it all together, we could say this then. We could say, since, let's just write it like this. The original series, the absolute value diverges. And then we can say a sub k converges. Then that's what verifies that we have conditional convergence. So we could say, therefore, the series converges conditionally. Okay, now these examples I did, this is the only one that you really got to do a lot of work on, the non-increasing terms, because it's not real obvious. So, if it's a fairly obvious thing, you can just explain, just like this limit right here. You can just kind of explain that, yeah, if k is going to infinity, you can disregard the 1. So for all practical purposes, this goes to 1 over k, which goes to 0. All right, so that's it. That's the examples I want to show for conditional and absolute convergence. So hopefully this helps you to understand how to do those tests. Again, always when you're doing a series test, do exactly what the theorem tells you to do. All right? Good luck.